Welcome to our comprehensive training on activated sludge process control. This presentation is based on the official training manual from the State of Michigan Department of Environmental Quality. Over the next 15 minutes, we will explore the fundamentals of wastewater treatment and the activated sludge process in detail. Wastewater is used water that carries pollutants away from their source. It originates from homes, businesses, schools, hospitals, and industries. Depending on the collection system, wastewater may become diluted with groundwater or surface water. Typical residential water use is about 100 gallons per person per day, while offices use 40 to 50 gallons per person daily. Hotels consume 400 to 500 gallons per room, and hospitals use approximately 200 gallons per bed each day. Components in wastewater can be classified as either inorganic or organic. Inorganic materials include sand, grit, minerals, and metals, which are not biodegradable. Organic materials contain carbon, originate from living organisms, and serve as food for bacteria. Solids in wastewater are categorized as suspended or dissolved. Suspended solids add turbidity and can be filtered out. Dissolved solids pass through filters. Total solids represent everything that would remain if water was completely evaporated. Settlable solids are particulates that settle under quiescent conditions. Colloidal solids are microscopic particles that remain suspended and give water a hazy appearance. Biochemical oxygen demand, or BOD, is a critical wastewater characteristic. As bacteria feed on pollutants, they consume oxygen from the water. The BOD test measures oxygen consumption over 5 days at 20 degrees Celsius. Total BOD equals carbonaceous BOD plus nitrogenous BOD. When untreated wastewater enters a stream, bacteria multiply rapidly, creating a zone of degradation. Oxygen consumption peaks in the zone of active decomposition, causing the dissolved oxygen to drop dramatically. This oxygen sag can harm aquatic life. As pollutants are consumed, the stream gradually recovers. Proper treatment prevents this environmental damage. Nitrogen and phosphorus are essential nutrients required by all living organisms. However, when discharged into streams and lakes, they act as fertilizers, accelerating aquatic plant growth. This process, called eutrophication, causes lakes to fill with sediment and vegetation over time. Excessive nutrient loads can choke waterways with weeds and deplete oxygen levels. Modern wastewater treatment plants are designed to remove these nutrients through biological and chemical processes. Nitrogen removal involves nitrification and denitrification. Phosphorus can be removed biologically or through chemical precipitation. The activated sludge process is a biological treatment method that uses microorganisms to break down organic pollutants. The process consists of 3 main components. First, the aeration tank, where wastewater is mixed with activated sludge and air is supplied to support bacterial growth. Second, the secondary clarifier or settling tank, where treated water separates from the biological solids. Third, the return activated sludge system, which recycles bacteria-rich sludge back to the aeration tank to maintain an active microbial population. This continuous cycle allows bacteria to efficiently consume organic matter, producing clean water and excess biomass that must be removed. In the aeration tank, several critical processes occur simultaneously. Microorganisms consume organic matter, converting it to carbon dioxide, water, and new cell mass. Oxygen must be continuously supplied through mechanical aerators or diffused air systems. The mixed liquor suspended solids, or MLSS, represents the concentration of microorganisms and organic matter in the tank. Typical MLSS concentrations range from 1,500 to 3,000 milligrams per liter. Maintaining proper dissolved oxygen levels, usually between 2 and 4 milligrams per liter, is essential for optimal bacterial activity and treatment efficiency. Operators monitor several key parameters to control the activated sludge process effectively. The food-to-microorganism ratio, or F/M ratio, compares the amount of incoming BOD to the mass of microorganisms in the system. Typical F/M ratios range from 0.2 to 0.5. The Sludge Volume Index, or SVI, measures how well sludge settles in the clarifier. Values between 50 and 150 indicate good settling characteristics. Solids retention time, or SRT, represents the average time bacteria remain in the system. Longer SRT values produce more complete treatment and better nitrification. Hydraulic retention time, or HRT, is the average time wastewater spends in the aeration tank. These parameters must be balanced for optimal performance. The secondary clarifier plays a vital role in the activated sludge process. Mixed liquor from the aeration tank enters the clarifier, where quiescent conditions allow biological solids to settle. Clear treated water rises to the surface and flows over weirs for discharge or further treatment. Settled sludge accumulates at the bottom and is collected by rotating scrapers. Most of this sludge returns to the aeration tank as return-activated sludge. Excess sludge, called waste-activated sludge, is removed to maintain proper MLSS concentrations. Clarifier performance directly affects overall treatment efficiency and effluent quality. Effective process control requires continuous monitoring and adjustment. Operators must maintain proper dissolved oxygen levels by adjusting aeration rates. The return-activated sludge rate typically equals 25 to 100% of the influent flow. Wasting excess sludge controls the SRT and prevents solids from accumulating. Daily laboratory tests measure MLSS, SVI, and effluent quality. Microscopic examination reveals the health and diversity of the microbial community. Operators respond to changes in influent characteristics, weather conditions, and seasonal variations. Proper control ensures consistent treatment performance and regulatory compliance. Modern activated sludge plants incorporate biological nutrient removal processes. Nitrification converts ammonia to nitrate in aerobic zones, requiring long SRT and adequate dissolved oxygen. Denitrification reduces nitrate to nitrogen gas in anoxic zones where bacteria use nitrate instead of oxygen. This requires a carbon source and careful control of dissolved oxygen. Phosphorus removal can occur biologically through enhanced biological phosphorus removal, or EBPR, which alternates anaerobic, anoxic, and aerobic zones. Chemical precipitation using aluminum or iron salts provides an alternative phosphorus removal method. These advanced processes significantly reduce nutrient discharge to receiving waters. Sludge bulking is a common operational problem where sludge fails to settle properly in the clarifier. Filamentous bacteria grow in long strands that interfere with compaction, resulting in high SVI values above 200. Causes include low dissolved oxygen, nutrient deficiencies, or high FM ratios. Solutions involve increasing aeration, adding nutrients like nitrogen or phosphorus, wasting more sludge to reduce FM ratio, or using chlorine to selectively kill filamentous organisms. Preventing bulking requires maintaining proper operating conditions and responding quickly to early warning signs. Foaming occurs when stable bubbles accumulate on the surface of aeration tanks or clarifiers. Biological foam results from nocardia or microthrix bacteria, which produce surfactant compounds. This thick, brown foam can overflow tanks and create operational difficulties. Chemical foam from detergents or industrial discharges appears white and dissipates quickly. Control measures include increasing SRT, adding anti-foam agents, using surface sprays, or implementing selector zones. Identifying the foam type and underlying cause is essential for effective treatment. Persistent foaming may require process modifications or source control. Wastewater treatment protects public health and environmental quality. Untreated sewage contains pathogenic microorganisms that cause waterborne diseases. Organic pollutants deplete oxygen in receiving waters, harming fish and aquatic ecosystems. Nutrients promote algal blooms and eutrophication. Toxic substances accumulate in food chains. The activated sludge process effectively removes these contaminants, producing high-quality effluent suitable for discharge or reuse. Treatment plant operators play a crucial role in safeguarding water resources for current and future generations. Their expertise and dedication ensure clean water for communities and healthy aquatic environments. We have covered the fundamentals of activated sludge process control, from basic wastewater characteristics to advanced nutrient removal and troubleshooting. Key concepts include understanding BOD, solids, and nutrients, recognizing the importance of aeration, settling, and sludge recycling, monitoring critical parameters like MLSS, SVI, FM ratio, and SRT, and addressing common operational problems. Successful operation requires continuous learning, careful observation, and responsive control. Thank you for completing this training. Remember, your work as a treatment